All right, hello again, Ling statisticians. Today we are going to move on to talk about two-sample t-tests. Having already learned about one-sample t-tests and paired sample t-tests, we're going to get kind of coup de grace here for the whole package by the time we're done. Before we get into that topic, though, there's a couple things I wanted to mention that were relevant to previous discussions in these lectures that I kind of forgotten about. And one of them is the source of the so-called replication crisis in social sciences. There's kind of a funny story behind it. There was a guy, a psychologist named Daryl Bem, who was relatively well-respected academic. I think he worked in Portland, at the University of Portland, maybe. I might have gotten that wrong, but he worked there for many years, and then around 2010, as he was kind of wrapping up his career, decided to publish a paper that kind of presented the accumulated evidence that he had gathered over his time in academia that ESP exists. Like, he had run various experiments involving subjects in the way that you normally do, and then gotten a number of statistically significant results showing that people could, either read people's minds or see what's going to happen before it happened, that sort of thing. All with, the crucial p-values of less than 0.05 for the relevant variables he was measuring in these experiments. And so he published this in a relatively well-known journal, who I think they just took a look at it and was like, well, this all checks out. He used the methods he was supposed to, as we say you're supposed to in, psychological science. And for that reason, we kind of have to just sign off on this and let the world make of it what they will. So this is from the Journal of Personality and Social Psychology, and this is the abstract for his kind of landmark paper about this, Feeling the Future, Experimental Evidence for Anomalous Retroactive Influences on Cognition and Affect. Basically saying, look, I've got scientific proof that ESP exists. And so he published this. Apparently, the people who know him or knew him, he's still around, but I guess not working in this field so much anymore. But the people who knew him as an academic kind of got the sense that he really believed this, that ESP is a real thing. He just needed to show the evidence for it. But that's not really the way this played out. People looked at this paper and what? This can't be right. There is no such thing as ESP. And there must be something else wrong with this, other than our beliefs that, there's no ESP, because there can't be ESP. So instead of that, what the problem has to be the methods that he used, and maybe the statistical analysis that he used to get this sort of evidence to try to prove that this was the case. So people have kind of attacked it from a variety of different angles. Number one, they tried to replicate what he did, the experiments he ran, and usually when they do that, I think actually maybe in every case that they do that, they don't get the significant results he did, which made some people suspect that he was engaging in what was called p-hacking, which is a technique that may have popped into your head after our discussions of hypothesis testing earlier. But one thing researchers can, in theory, do, even though it's not statistically kosher, is to say, well, you're going to run a study where you're trying to see if there's a significant difference between two groups in whatever sort of task. And, maybe you've got planned that you're going to run 25 subjects in this study, but say you've run 12, you want to take a look at the data, and you look at the data and it shows you that you have a p-value of 0.02, which is a significant result. And at that point you say, I don't need to run anymore. I'm just going to roll with this because I've got a significant result now and I can publish it and all is good and dandy. Or maybe you can do it a different way and say, I'm going to plan to run 25. I'll take a look at the p-value when I've run 15. Oh, it's not significant. I'll look at it again when I've got 18. Not significant. Look at it again when I've got 21. Oh, significant. Now with 21, I'll just stop there. And I've got my p-value that I need, right? That's p-hacking. So you're just kind of running the experiment to get the result rather than just sort of honestly running what you planned and just going with whatever the data tell you at that point. So that's effectively cheating the system, the null hypothesis significance testing paradigm. And that is something that can lead you to a lot more false alarms than you should get according to the rules of the game, basically. So it's possible he was doing some of that and just kind of collecting those p-values over time. It's in theory, it's possible that ESP exists, but probably not, right? And so Daryl Bem kind of wound up not having the influence on the field that I guess he may have hoped to have. So what it has made us do is just analyze the sort of structure of how we run stats in social sciences. And I think it's kind of winding up being for the better overall. And scientists generally still don't believe in ESP, but I'm going to set that aside and let you know what we do believe in now. One approach that people have used more recently to try to get over this idea that you need to have like a significant p-value to publish anything meaningful in your career is one approach that I've engaged in and I've seen other people use is called using registered reports. So normally, like if you submit a paper to a journal for publication, you've completed the entire experiment. And then, since you know that they're probably not going to publish it if you get a null effect or a null result, you probably are submitting something that has some significant statistical effect in it somewhere. So the whole thing's completely done. You've run you designed the whole study, you've run the experiment, you've done the statistical analysis and written the whole thing up. And you say, here, what do you think of this? Would you like to publish this? And then they send it off to peer reviewers who say, it looks like this is done right, like this, Daryl Bem ESP study. So because it looks like it was done right, they have to, publish it if they think it's something of interest to their readers. But registered reports kind of stops halfway in that process and says, you're an academic or a researcher and you design a study and you say, I'm going to collect this data and I'm going to use this statistical analysis on it. Does that idea look good to you, peer reviewers of the world? And that you submit that plan to the journal and then they ship it off to peer reviewers who kind of double check your methods and your stats. And you get that all cleared out of the way before you run the study. And then you run the study and you get some results from it. And they may be significant, they may not be significant, but either way, the journal will commit to publishing it because it doesn't want to just be biased to publishing the sort of significant results when, if you've done the experiment properly, the results will be valid and maybe of use for anybody who wants to read it regardless, right? So that's another way to kind of deal with this problem so that you're not just sort of like looking for significant p-values wherever you go in the world of scientific research, right? So this is still kind of an ongoing and developing situation, I guess you could say. I think Daryl Bem published that paper about 10 years ago, if I go back to that link I had here. This is from 2011. So people are kind of still working out what all this means and trying to come up with better processes as we go. But like I said in one of the earlier lectures for this class is stats is always changing. Like our field is linguistics, is always changing in its own way, and then stats is changing in its own way as well. So you kind of have to keep up with both to a certain extent. And then, psychology is going to change too as well. You have to keep up. It's like that quote from Einstein about how, life is a bicycle. If you're not moving forward, you're going to fall over. That's just the name of the game. I've got another, this is a bit of a distraction. This is somebody writing a letter about why the journal that Daryl Bem published that study in should retract it, which may be so, although at this point it's a bit of a historical document. I wanted to show you another link that I found. This is a more general audience article from slate.com about this whole mess from about 4 years ago. So you could check that out if you want. You can also check out the original study here if you'd like to as well. Either way, I'm going to move on and talk about t-tests today, and specifically TwoSample Ttests. So we've already talked quite a bit about hypothesis testing, and we looked at these two different kinds of t-tests, one-sample t-tests and paired-sample t-tests. And today we're going to learn about two-sample t-tests and how we use those to test a hypothesis as well. So I think these t-tests are helpful in terms of trying to basically understand the foundations of how the testing paradigm works, the hypothesis testing paradigm works. The math is relatively simple for these. Once you get into the two-sample t-test, the math gets a little more complicated, but we don't need to focus on it so much because we're just basically expanding on what we already know to deal with two samples rather than one. And what I mean by two samples is if you take data from two different groups, which you want to know, do they exhibit kind of the same behavior or different behavior? Are they part of the same population or not? So on the surface, at least they're different. Like, let's say I calculate or collect VOT measures for, speakers of Canadian English from Calgary versus speakers of Canadian English from Edmonton. Are they the same or different? Who knows? So this is probably going to be the sort of t-test that you will use most often in your career, because often people like that sort of compare and contrast sort of idea when they're doing a research study, rather than like, well, is the VOT of Calgarian English equal to 100 milliseconds or not? That's sort of not as exciting, generally speaking. So with that in mind, let's get into it and see how these things work. And like I said before, the logic behind the t-test is relatively simple, but the math you need to get it to work is a little more involved than what we've seen before. And the way I kind of want to approach it is to just go back to this visual of a hypothetical sampling distribution. So remember, because this is a sampling distribution, this kind of normal curve here will represent the means of different samples. And when we run an experiment, all we do is get a tiny little picture of this sampling distribution. So we start off with like one sample mean from wherever. So let's just pretend, let's keep going with that idea of, let's look at VOT from Calgary versus Edmonton. Let's say Calgary's VOT is at 94 milliseconds. That's the mean VOT got for your Calgary speakers. And then you collected VOT from a bunch of Edmonton speakers, and they turned out to have a VOT of about 102. And the question is, well, are these two means, or these two samples, reflecting different underlying populations or not? Or are they just part of the same sampling distribution? What's the likelihood that they could both fall on the same sampling distribution, such that they're not really significantly different from each other, that they reflect the same underlying population somehow? So yeah, that's the question I have here. How likely is it that both sample means came from the same sampling distribution? That's the question that a two-sample t-test is going to answer for us quantitatively, so that we don't have to just eyeball it and say, I think they're different. Maybe Edmonton, Calgary, totally different, right? Maybe. Okay, so what we do is we answer this question by generating a t-score that reflects the distance between the sample means on the sampling distribution. So if you remember, if I took just one of these guys, say I had a mean of 94, and I calculated, going back to the z-score calculation days, I would look at the sort of the difference between that sample mean and the overall mean of the distribution, and then kind of normalize that by saying what is the difference there between my sample mean and the population mean in terms of standard deviations, right? So you can still do that if you're looking at sort of the difference, not between the sample mean and the population mean, but this sample mean and that sample mean. That's the distance or difference that we're going to be focusing on here. How far apart are these blue and red dots from each other in the sampling distribution itself, in terms of the sampling distribution standard deviation? That's kind of the crucial standardized unit we use to measure that distance. So the problem here is that we can't assume a uniform scale for determining that t-score in terms of standard errors, or that standard deviation of the sampling distribution, if the two samples have different standard deviations. So just to kind of review, I'm taking two samples. Here's my Calgary VOT, here's my Edmonton VOT, and I can calculate the means of those VOT samples, and they put me in these spots on the sampling distribution. But then, if you remember, from those samples, I can calculate the standard deviations of those samples as well. And presumably, if they're coming from the same underlying population, their standard deviations should be roughly the same as each other. But if you see wildly different standard deviations in one versus the other, then that's starting to give you a clue that you kind of can't assume the same underlying standard deviation for the entire population. And this sort of calculation becomes more problematic. So we kind of have to look at that a little bit. There's various ways around the problem if you get standard deviations which are significantly different from each other, but I'll walk you through the process of how to determine that. And just for now, we'll at least consider the potential problem that one of these samples might have a different standard deviation than the other, and ideally they won't, because then applying this test or this paradigm is straightforward, because you can assume there's a common variance shared between the two samples. There's a common variance in the population which doesn't change meaningfully from one sample to the next. Okay, hopefully that makes sense. But the way we're going to approach it is to learn this test called the FTest, which can test whether the variances of two samples are the same or different. or significantly different from each other, as it were. Okay, so this FTest, the F here stands for Ronald Fisher because he came up with this. And so what it does is basically going to tell us whether the variances of two different samples are different from each other by calculating the ratio of those variances first. Before I get into that, this is a question I always ask in class, and as long as we're here, I'll ask it again. Like, how do we calculate variances? What's the equation for that? I think you may have heard me say this about 2 or 3 times already, but what's the answer, class? The answer is the variance is equal to the sum of squares, or squared differences, divided by the degrees of freedom. Remember, Ronald Fisher also came up with this idea of degrees of freedom. So this all kind of ties together in the end. It was just Mr. Gossett, who came up with the t-test that we're going to play with at the end of this lecture. So the way the F-test works, like I said, it's basically going to calculate a ratio of variances from two different samples. And then it's going to see where that ratio fits on something called an F distribution. So for z-scores, we had normal distributions. For t-scores, we had t-distributions. For these F ratios, we're going to have F distributions. But these are different because they don't look all that normal. We're getting something different than just like sort of a distance score. We're getting this like ratio between two different variances. So those wind up on a distribution which is not normally shaped, although it kind of has that bell curve shape to it. It has this long tail over here to the right. It's clearly skewed far to the right. And then it also kind of has a limit here over at 0, right? So you can think about this, in terms of ratios again. So like if you have variance A divided by variance B, if variance A is bigger than variance B, you're going to get a number bigger than 1. And that can extend far out there. So like if my variance of A was 100, my variance of B was 1, then I have a ratio of 100, right? So that could extend way the heck out to the right of this tail, right? But on the flip side of that, if I just randomly had it calculated the other way, where I had variance B over variance A, then I've got 1 divided by 100. So then I've got a value of like 0.01 way down here somewhere. But I'm never going to get smaller than 0, right? So variance is something from 0 on up. And that applies to both the variances we're looking at. The smallest number possible I could get is 0. The biggest number I could possibly get is basically out there to infinity or undefined if I have no variance, I guess. But either way, you should expect these to be centered relatively around 1. That's when the variances are equal, and you just have not very much space between 1 and 0 compared to like how much space you have above 1 for the ratio of these variances. And that's kind of why this distribution shape winds up looking the way it does. It changes, though, its shape a little bit according to how many degrees of freedom there are in the samples you take, or basically how many observations there are in each sample. So you might notice here I've got a couple different things from what we've seen before in R. Instead of looking at a dt or a d-norm function, I'm looking at a df function here because we're using an F distribution. And try not to get that confused with the degrees of freedom for both samples here. So these parameters specify how many degrees of freedom there is in sample number 1 and how many degrees of freedom there are in sample number 2. I put 7 in both just to kind of keep it simple, and I'll change that as I show you a few more examples, but these don't have to be equal to each other. Just it's a little bit easier to understand the whole concept if they are. Yeah, but like this could be 5 and this could be 7 if you want, and I'll show you at least one example of that as we go. So here's a few more F distributions. Here's one with 3 degrees of freedom in both samples, and then I'm going to make this one blue just to set it off a bit from the original, which was black. And if we look at that, we see the whole thing shift a little bit over to the left here, so closer to 0. And I'm not exactly sure why that happens with fewer degrees of freedom. It just does. Like I said, the balance point is still probably going to be somewhere around 1 for these, because that's where you expect them to be equal to each other. If I make more degrees, or I put more degrees of freedom in each sample, or more observations in each sample, then I get something really big, which actually goes off the top of the screen, but it's here in green. Again, relatively close to 1 in the middle here, with this long tail over to the right. And then here's one in orange. I'll do one last one. This is with 6 degrees of freedom. I'll do one last one where we don't have the same degrees of freedom in both. So the orange one is kind of in the middle here. Let's do one where we have 6 in one sample and then 9 in another. We'll make that red. It's going to be relatively close to the orange one, but it pops up here a little bit. But they're all in the same neighborhood. It's hard to actually kind of push it away from that so much because like I said, it's generally going to be centered around 1, and it will only not be, I guess, if you have sort of more extreme values of degrees of freedom, like closer to 0 or much bigger than like 7. Either way, that's what it looks like, and what we're going to get out of this is some ratio of the variances, and we're going to find out where it is on these curves, and then we can determine like what proportion of this distribution is like to the right or to the left of this particular ratio, right? And that determines our p-value for the f-test. So basically, if I wind up here close to 1, a big chunk of the distribution, no matter what shape it has exactly, a big chunk of that distribution will be to the right or the left of that f statistic. So I will probably have a p-value bigger than 0.05. But if I get way out here in like the tail, then there's maybe less than 0.05 of the distribution to the right of this, or maybe over here, there's less than 0.05 of the distribution to the left of this. In that case, I might have variances which are statistically different from each other because they're pretty far away from the 1 ratio, right in the middle. Hopefully that makes sense. And I guess the last thing I'd say, in case this question has popped into your head, is you don't know ahead of time like which sample is going to have the bigger variance. So you don't know if you're putting the bigger one on top or the bigger one on the bottom. So for that reason, you don't know if you're going to have a ratio bigger than 1 or less than 1. And so you kind of have to be able to deal with both tails at the same time with this test. And that's why we have to look at both halves of this. So that, it's nice to be able to organize things. Why don't we just make it bigger than 1 all the time, and then we can kind of easily conceive of how far away it is from 1. But like I said before, you don't want to know everything going in ahead of this time. You don't want to know everything about your stats ahead of time going into like this process. You have to let the process just like tell you what it finds out from your data. Otherwise, you're kind of cheating the system. So I'm going to show you how this works a little bit with some weather data. We've seen this before when we were playing around with the conversions between like Celsius and Fahrenheit. And this is something I have thought about a lot living in Calgary, having come from the Midwestern US, which has sort of more stable weather or climate than Calgary does. A climate which is more stable, a climate which gives you more stable weather than Calgary. Calgary is this weird like up and down place, both economically and climatically. And I'll show you that through this collected weather data. So I put this together the first time I taught this class 10 years ago. And I got it from all this weather data from the Environment Canada site, which was well organized at the time. But since then, they just like stopped updating. So I'm stuck with data from 1881, which is when Calgary was founded, to 2011. And I've got it in here. Yes, here. We've seen this before. But it hasn't been updated since 2011, sadly. But this is all the high, low, and mean temperatures for Calgary for like every day in its existence. And some similar data from Toronto down here at the bottom. Okay, so Toronto's climate is more like the climate I grew up in, like in Minnesota, Illinois, so on and so forth. And we'll see how it meaningfully differs from Calgary here in a second. So right. Sorry about this joke. But when I moved to Calgary, I'll just pause here for a second. When I moved to Calgary 14 years ago, I would see these like political signs everywhere that would say like more Alberta, less Ottawa, because Alberta is so oppressed by the federal government. And maybe that hasn't changed, but we'll see what else is different here between Alberta and Ontario. I want to start off by just subsetting out the high temperatures for Calgary and Toronto in both January and July of 2011. I'm not going to walk through the details here because I think you will understand them if you take a close look at them, having done a few homeworks for this already. I'm just going to spit them out each into their own separate vectors here. I'll show you one. It's basically going to give you like 30 high temperatures here for Calgary in January 2011. And then I will show you the means of those 4 little samples for our 2 cities and our 2 months. So for July of that year, which should be the height of summer, Calgary's average high was 22.69 Celsius, which for those of you living in Fahrenheit land is about 72 degrees Fahrenheit, which I guess is nice, but not super hot. Toronto's was 30.1, which is about 86 degrees Fahrenheit. So that's, for me, genuine summer weather. We can also take a look at their average highs in the winter or January of the same year. For Calgary, it was negative 4.1, which again in Fahrenheit is about 25. And then Toronto's is negative 3.2, which is about 27 or so. So those are pretty close in January, but there's more of a difference here, at least superficially, in July. So bigger difference in summer than in winter, at least in terms of average highs. I guess I'll also preface this by saying that I have a brother who's really into the weather. I'm kind of into weather like data. He's really into it, and he will often call me up and say what the average highs were for Calgary in a certain month or year or whatever. And I was like, yeah, averages don't mean that much for Calgary. So where does that come from? And I'll show you a little bit about the variance we get in these same data sets for the 2 cities and the 2 months. So looking at July's weather 10 years ago, this is just the variance. The specific numbers don't mean a whole lot, but it's 11.6 for Calgary, 11.2 for Toronto. So it's pretty close. And that's in the summer. We can also, even though in the summer Toronto was warmer than Calgary on average, we can also look at the variances in the winter. So as we spit out these numbers, we see that Calgary has a much bigger number in terms of variance than Toronto does, so 122 to 18. And for those of you who don't live here in Calgary, Calgary has this really interesting meteorological phenomenon called the Chinook, which is where this wind blows over the mountains, which are to the west of us, and as the wind descends down into the plains where Calgary is located, it heats up, and it suddenly can get warm just on a moment's notice, basically, whereas other times in Calgary, we get these north winds coming down from like the Northwest Territories, or hey, Edmonton, and it can be extremely cold. So we have this sort of, alternating like really warm days versus really cold days in the winter. And when I say really warm days in Calgary in the winter, it's not that warm. It's like around freezing or so. But still, it's better than like 20 below, whether that's Fahrenheit or Celsius. In Toronto, things are a little more stable than that. Stabler, like Ken Stabler. But here's the moral of the story. Toronto is warmer than Calgary in the summer, but has about the same mean temperature as Calgary in the winter. In the winter, though, because of this kind of weird alternating Chinook versus north wind situation, Calgary has a much larger variance in high temperatures than Toronto. And you can really see this if we plot this out in a box plot. Yeah. So if you take a look at that, it'll erase our F distributions, but it'll show us where these high temperatures are located in the Celsius scale for both cities. So like I said before, in July, Toronto is warmer than Calgary. In January, if you look at just the means or the medians, actually the median, Calgary is a little bit higher than Toronto for this particular data set. But this variance is obviously much bigger for Calgary. So isn't that kind of fun? Yeah, it can make it hard to plan on what to dress or how to dress for the day. I'm also going to show you some histograms of these temperatures. So I'm going to make it relatively simple, just put 4 breaks in it so you can kind of see how it lines up. This is Calgary's histogram of high temperatures for January 2011, and I've got it to negative 30 here on the low end. So we do have days where it doesn't get above negative 20, or maybe even worse than that. So yeah, it does definitely get cold, but also we can have warm days, right? So between like 10 and 20, that's above 50 degrees Fahrenheit for those of you living in Fahrenheit land again. So your high in Calgary could be above 10 degrees Celsius, or it could be below negative 20, the high temperature. So yeah, it can be a little rough sometimes, but it's not that bad. In Toronto, though, everything's a little more condensed in terms of where you can expect the high temperature to be. So sometimes, or rarely, you get high temperatures of below -10. Sometimes you get them above 10, but normally the high temperature is going to be between -5 Celsius and 0 degrees Celsius, which is about 23 to 32 Fahrenheit. What I really want to kind of focus on here, though, is this variance issue rather than the means so much. And before I show you the results of this test, again, when we use t-tests to try to analyze data, what we're doing is comparing means. Like in that sampling distribution I showed you, I showed you 2 spots, and we're basically trying to figure out whether those means are different from each other or not. So we don't think about the variance so much, but that's part of the equation, right? Because that's how we measure the distance between those means. And if I take a look at this FTest, or this variance test in R, comparing the variances in Calgary for January 2011 and Toronto for January 2011, I get a very, very small p-value of 1.6 times 10 to the -6. So that's 0.000000016, something like that. So it's a very small number. The F ratio, the ratio of the variances, is about 6.569. So that's 122 divided by 18. This tells me the degrees of freedom. This tells me where the confidence interval is for that F number, that F ratio. And then it kind of repeats the ratio of variances down here again. But basically what it's saying is my p-value is so small that it is highly unlikely that these two variances come from the same underlying population. The true ratio of variances, therefore, is not equal to 1, or in other words, these two cities probably do not have the same sort of variance in high temperatures in the winter time. We can compare that to what we see for the July data. We get the same sort of readout here. We get an F ratio. So this is where, if we go back, this is dividing like 11.6 divided by 11.2. So that ratio is 1.04. Which is not very different from 1. The p-value turns out to be 0.9128. Yeah, so we don't think this is a significant effect. We don't discard our null hypothesis here, so we reject this alternative hypothesis and say, yeah, these variances are basically the same. The ratio of variance is probably 1, or we can accept that hypothesis for now without any further reason to doubt it. So in July, what that means is that the variances for Calgary and Toronto are basically the same. In January, though, they're different. And in January, that means we're going to have kind of an issue trying to compare our mean temperatures for the two cities, because they're kind of coming from not equal playing fields, as it were. We can't use the same sort of unit of distance measure between them when we're looking at how they fit onto a sampling distribution. So this is the question I have at the bottom of this slide. What does this have to do with t-tests? And that's what it has to do with t-tests. We have to kind of make sure the variance is the same. Otherwise, that t-test approach won't really work. I'll show you how we do this in that sort of July 2011 case where we inferred that the two samples have equal variances, or at least not significantly different variances. This is the simpler case, and I'm going to walk you through the math for this. But again, I'm just kind of trying to situate the math, which is found in the textbook in terms of like the concept of how to run this test. I'm not going to test you on the specific details of the mathematical equations or anything like that. I'm just going to try to explain them in case you were wondering exactly what they meant or you couldn't figure out some specific details about them. So how we get into the math is that if we have samples which have more or less equal variances, but they have different means that we want to test in this t-test paradigm to see if they're significantly different from each other, we have to combine the variances of the samples to calculate our t-statistics. So basically what we're doing by combining the variances is coming up with like an estimate for what that sampling distribution standard deviation will be, that standard error that we use to calculate the t-score. And luckily for us, somebody else has already worked out this math. We don't have to do it from scratch. And like I said, these equations are in your textbook. And if case you looked at them and got glassy-eyed and said, I don't know what that means, I can explain it to you on basic terms. But this is an equation for what is called pooled variance. So, excuse me a second. But if you remember, S squared was how we represented variance. Here it's S squared sub P, or S sub P squared, I guess. That's the pooled variance for two sample t-tests, with S sub A squared representing the variance for sample A, and S sub B squared representing the variance for sample B. N sub A is the number of observations in sample A. N sub B is the number of observations in sample B. Did I say that right? Yeah. Number of observations, sample A, number of observations, sample B. And so when you subtract those by one from those, you get the degrees of freedom in the, the Ronald Fisher conception of how those work. And so this is the equation, and just spitting all these things out here. Yeah, the individual variables look familiar. How does this all fit together? It's actually pretty straightforward once you take a close look at it, but I don't have room to explain it on this slide, so I'll show it to you on the next one. But basically what we get here is, if you remember, variance, or S squared, is equal to the sum of squares divided by the degrees of freedom. So if I have like the variance for A, sum of squares of A divided by the degrees of freedom of A, and then I multiply that by the degrees of freedom of A, which is N sub A minus 1, it basically cancels out that degrees of freedom factor up here in the numerator, leaving me with just the sum of squares for both samples. So I have sum of squares for A plus the sum of squares for B, and then I'm dividing that by the degrees of freedom for A plus the degrees of freedom for B. And that should hopefully stand to reason. We said variance is equal to sum of squares divided by the degrees of freedom. I'm just adding both samples on both the tops and the bottoms of this equation to get my pooled variance value. Okay, so in case that wasn't obvious for me just saying it, here I can show it to you in writing and also in equation format here down at the bottom of the slide. And pardon me, I need to get another drink of water. But basically, this is giving us our pooled variance measure, and we can use this to try to calculate a t-score in our t-test. We have to go one more step to do this, though. As you might recall, when we were calculating like the relevant z-scores for a z-test, so-called, you have to divide by like the standard. You have to divide the distance between your sample mean and the population mean over the standard error for your sampling distribution, or at least your estimate of the standard error for the sampling distribution. And the way you do that is on the bottom of the equation, you divide the standard deviation by the square root of n, the number of items in your observation. That was for one sample t-test. Since we're doing two sample t-tests, we're going to expand on that just a little bit. What's in the numerator here is the difference in values between the mean of sample A and the mean of sample B. And then I divide that whole thing by the square root of the pooled variance divided by the number of observations in sample A plus the number of observations in sample B. And if I simplify that a little bit by kind of taking the square root of this stuff in the denominator, that gives me in the end the standard deviation, the pooled standard deviation for both samples divided by the square root of the number of items in those samples, which basically is what we saw before with standard deviation divided by the square root of n, but here we're adding the two numbers of items together to get this equation for t in the two-sample process. Basically, though, what we're doing is we're looking at the difference in value between those two sample means, like the red sample mean versus the blue sample mean, and then dividing it by this kind of unified distance measure, which is the standard error or estimated standard error for our sampling distribution. And hopefully that makes sense, but what we wind up getting out of this is a t-value, which we can put on a t-distribution to generate a p-score for our testing paradigm. And from that p-value, we can draw inferences about whether we accept the null hypothesis or reject it, like we've done before. So here's this. I'm just going to take a brief math breather, but here's the implications of what we're doing. We calculate a t-score with this equation, and you don't have to do the math by hand in this class. You can get R to do it for you. So that's just where it's coming from, but you're going to see a number at the end of the day. And from that, you can derive the corresponding p-value based on the t-score and how it fits onto a t-distribution with a certain number of degrees of freedom, which is n-1 in this case, although we're going to have to tweak that a bit because we're getting values from two different samples here. The p-value will then tell you whether your sample means are significantly different from each other, and that will normally happen when p is less than 0.05 because this is where we set alpha to be conventionally. You can tweak that if you want. We've said that before, but for normal cases, it's going to be 0.05. And then if that's the case, if you do get a p-value of less than 0.05, you conclude that the sample means could not have come from the same sampling distribution, and in fact that they reflect different underlying populations. So in that case, if you look at like the Calgary VOT mean versus the Edmonton VOT mean, and you get some big t-score, which leads to a very small p-value, you say, oh, look at that. Calgary speakers are different from Edmonton speakers because their VOT values are not the same. They're significantly different. Okay, that's a refresher of how this process works in the end, with this added element of where the t-scores come from thrown in. That's all I'm going to say about the basic case. If we have the other case where the FTest shows us that the variances of the two samples are significantly different from each other, we have to do the math slightly differently. And this is also shown in the textbook. And this is also something I don't want you to worry about unduly. But just to kind of give you a sense of where the new numbers are going to be coming from, I'll show you the equations we use to calculate them. And for the most part, it's going to have an effect on the degrees of freedom more than anything else. So first of all, you don't pool the variances in the same way. Instead, you just keep the variances separate from each other and you calculate the standard error kind of as you might expect. Whereas before in the one sample case, we had a standard error of the square root of variance over n. In this case, we have two samples, so we have the square root of the sum of the variance of A divided by the number of items in A plus this variance of B divided by the number of items in B. That's not too complicated or too hard to understand. What is less intuitive is figuring out how the degrees of freedom are calculated for the t distribution in this case. And this is the equation that you use apparently. And again, I'm glad that the statisticians have worked this out over the years so that we don't have to. And we don't really even have to like pretend that we understand this. All these little variables look familiar, like the variance of A, variance of B, the number of items in A, the number of items in B, so on and so forth. Degrees of freedom, whatever. This is where the degrees of freedom will come from. They're not going to be a nice and simple number in most cases like we see with the equal variance case. It's going to be something complicated, probably with a decimal point and some numbers after it. But that's basically where it's coming from. You don't really need to worry about things much more than that. When you do take this approach, though, it's known as the Welch correction for the two-sample t-test, and R will report the results of the test to you with that notifier as part of it, that it's using the Welch correction. And I will also say that R uses the Welch correction by default. So this is kind of a more conservative way to run the test. So if you're just not being careful with your t-testing procedures and you forget about considering whether the variances of the two samples are the same or not, then you will wind up running this test, which assumes that the variances are not equal to each other or that they are significantly different from each other. So it kind of like is a check on your carelessness by using the more conservative option if you aren't doing your homework and checking the variances to begin with. Yeah, so I'll show you how this works in R, and we'll just run this t-test command for our two sets of high temperatures here. We'll go back down to the bottom. And this is what it looks like when you actually run one. You'll probably run a few as you go through this class and also for the rest of your life if you keep up with academic research or whatever you're doing. So again, I'm comparing the Calgary highs to the Toronto highs in January, which we said before were fairly similar. Actually, we can see them down here. So Calgary's average high in January was negative 4.2. Toronto's was negative 3.2. On the surface, those don't look super different from each other. If we do the math for the t-test, we find that the t-score is about negative 0.47. And the negative here just means that Toronto's is bigger in value than Calgary's. If I were to do it the other way, I'd get the exact same result with a positive t-score. So don't read too much into the sign there, but you can read something into the quantity. So as I said, it's positive here. It's otherwise the same. The degrees of freedom were calculated in that complicated Welch correction way. And as I said, it tells you this is a Welch two-sample t-test that we're running. And then because this t-value is close to 0, it's kind of in the middle of the t-distribution. So the p-value winds up being relatively big, or most importantly, bigger than 0.05. So we don't reject the null hypothesis in this case, and we basically say, well, Calgary's mean high in January is basically the same as Toronto's mean high in temperature in January on average, right? So I'm not going to say more about that than that. You can kind of get a sense, I guess, of how big that standard error is. So if I'm subtracting like this from this, I get a difference of about 1. That's on the numerator of the t-score equation. Then I divide that by about 2. So my standard error is going to be about 2 here, which gives me a value of about 0.5 at the end of the day. Again, you're normally not going to worry about this too much. Normally just take a look at the p-value and say, is it significant or not? And you will find a significant value for p if you run the t-test with the July data from the same cities. And here my t-score is not 0.5 or whatever. It's negative 8.6. And these are my Welch corrected degrees of freedom. That converts to a p-value of a very small number of 4.35 times 10 to the negative 12. So that starts off with 11 zeros. I'm not going to say them all. It's just the important point is it's less than 0.05. So you got a significant result here. This number, 30.1, is significantly different from this number, 22.7. The average high in Toronto in July is probably going to be higher than the average high for Calgary in July. And I was just looking, we're kind of in between July and January. Today's October 2nd. So right now we have a temperature of 14 Celsius in Calgary and it's 25 in Toronto. So there you go. It's just a warmer place. It'd probably be a pretty nice October day in Toronto if we were there. Instead, you can kind of feel winter coming on its way here in Calgary. So that's okay. We've had a beautiful fall so far. I will point out, though, that the highs for Calgary in January of 2011 were not in any obvious way normally distributed, or at least it was, a bit of a stretch to say that they were. So we were looking at these histograms before, and I can show you the one for Calgary that we saw a moment ago. Is this normally distributed? Yeah, maybe. It's a bit of a stretch to say that. So that's just the distribution of the sample, but it could potentially have an effect on how we actually run the t-test itself. I'll give you some guidelines on whether it's okay to run a t-test here at the end of the lecture, but just keep that in mind. The actual shape of the sample distribution matters to some extent when you run these things. But like I said, R kind of takes care of you in a way by trying to make the test more conservative if you're not careful about it. So it defaults to the Welch correction when it runs a t-test. If you don't want to run it with that Welch correction, then what you do is specify that the variances are equal when you run the t-test. And I'll give you an example of that twice. And the specific code you use there is var.equal equals t, capital T, which stands for true. And so we're saying the variances are equal, and when we run the test, it gives us basically the same results here. Basically, I think the exact same t-value, different degrees of freedom, because these aren't Welch corrected anymore. But the only difference that makes is in terms of the p-value. So for this one with the equal variances, it's a slightly smaller p-value than what we got before. Like I said, this Welch correction is a little more conservative, and in being more conservative, it's going to usually prop up the p-value by a little bit to make it less likely that you will get a significant result when you shouldn't, to make it less likely that you will get a false alarm of some sort. I'm going to try the second one here, and we get basically the same result here as well. Slightly different degrees of freedom leading to slightly different p-values in the end, but these are also clearly significant results because this p-value is much, much smaller than 0.05. So in the summertime, Calgary and Toronto have different high temperatures. That's all that means. Yeah. Okay, we'll look at Calgary and Toronto VOT again in some future day, maybe. I will also point out that when you use the variance equal setting, the Welch in the report of the t-test results disappears. I didn't point that out, but before we had Welch TwoSample Ttests up here. When we do it this way, we just get TwoSample Ttests, right? So in case you didn't notice that, that's a little subtle difference between the two. And as I mentioned here, otherwise, the biggest difference between the two sets of results is that the degrees of freedom become larger in the equal variance test. And I already kind of did this for a couple of these. I was talking a little bit about the power of the t-test options. But what I mean by that is that some t-tests are more likely to give you a significant result than others. since the p-value for the variance equal setting is usually going to be smaller than the p-value we get for the Welch correction, that's a slightly more powerful test in the sense that it can give you a significant result more often. But by the same token, it's probably also going to give you more false alarms. So be careful about that. We can also check the paired samples t-test, which approaches this in a totally different way, right? Because it's just subtracting the mean highs between the two cities and then creating a one sample test t-test out of that. And for this one, we get degrees of freedom of 30, and our p-value is 0.6166, which is even lower than what we got here for the variance equal test. So that one's going to be a little bit more powerful because we're kind of just assuming the only difference here is based on the city. These are all the same days that we're looking at in January 2011, so we can kind of just cancel out those differences and focus just on one location versus the other. If you can do that, you may get a smaller p-value. You may get a better chance at getting a significant result and, publishing your groundbreaking data on Calgary and Toronto weather at the end of the day. So that's all I'm going to say about that. There's one last kind of finishing touch here that I'll mention, is that when you make a box plot in R, you can add a parameter called notch equals t. And I'll show you how this works. So I didn't go through this code before because it's all pretty familiar. These are just the data sets where we're getting the numbers from, and then some labeling here. But at the end, I'm putting this notch equals t into the command. And what that does is it's going to make these box plots. Somebody in their homework called these box points, which I kind of liked. It's making these little boxes with a notch in them. And so the way, I'll go back in history again, but the way I was trained kind of informally, like in the 90s with stats, is that we would normally like plot means with like the standard errors as little, like these dynamite plungers on top of them. And the idea was supposed to be that if your standard errors for two different distributions are overlapping with each other, then you don't have a significant difference. I actually don't know if that's technically true or not. That's just kind of the way we looked at it. This approaches it in a slightly different way. It's giving you kind of the same sort of range for the t-test distribution. So it's putting these little notches in the boxes so that they squeeze into the middle here, like they're going into somebody's waist, I guess. And the idea is if these notches don't overlap with each other, like you see up here for the July data, then you have significantly different distributions, or your samples are significantly different from each other. There is overlap here, obviously, between these notches and these notches. This one has a pretty big range, of course, but that means that there's not a significant difference here. At least in theory, that's what it's supposed to mean. Don't bet the farm on that, but it's just kind of a nice way to kind of give your readers a sense of what sort of relevant variation there is in your mean calculations for these samples, if they can see sort of these notches as they look through the graphs in your paper. So I'm not going to say anything further about that. I think I'm going to wrap this up. I think I'll just roll on through. I'm a little tempted to split this into two videos, but I'll just make it one big one. And you can pause and rewind and do whatever as you need to. But at the end of this, I want to give you a user's guide for when you can use t-tests, including giving you an option for not using a t-test at the end of the day if you can't sort of satisfy some of these guidelines that I'm getting pretty much directly from the Introduction to the Practice of Statistics textbook. So for starters, there's a couple of things you should consider when you run a t-test. The first is whether or not your population distribution is normal or not. And that's an interesting case. Even if your population distribution is not normal, you can still use a t-test because the sampling distribution itself should become normal according to the precepts of the central limit theorem. So I think we tried this out where we looked at like the F0 data, which was strongly skewed right. And then if we take lots of samples from it, then we wind up with a sampling distribution that's normal. And if the sampling distribution is normal, then we can kind of calculate distance in the distribution in terms of like the standard deviation in the sampling distribution, which is basically where we get t-scores from, right? That's only going to work if we're dealing with a normal distribution. And like I said, we luck out with this, because if n is large enough, then the central limit theorem will kick in, and it will make that sampling distribution itself normal, more or less. So as usual, it helps to have a sufficient number of observations in your samples. Rather than having like 3 observations in your sample, maybe you can get like 20 or 30 or so on and so forth. But I'll give you specific guidelines about how big your n should be as we go through this little user's guide. Another consideration to worry about is that t-values are not resistant to outliers, because remember, we're comparing means here, the mean of sample 1 versus the mean of sample 2, and means can be pulled in one direction or another by outliers. And in fact, that was kind of an interesting little thing here I noticed before. Yeah, if we go back to here, we looked at the January means, and in terms of the means, Calgary's mean temperature was a little bit lower than Toronto's, but if you look at the medians, in the box plot, Calgary's median is actually higher than Toronto's. So Calgary's mean was probably pulled down by some of these terrible like days where we never get above -20, that sort of thing. So be careful about that. Remember, with a t-test, you're comparing means and trying to determine whether they fall on the same sampling distribution, which is derived from the same underlying population distribution. And you can also apparently run into problems with a strongly skewed distribution, because that will pull the means in one direction or the other, in the direction of the skew, basically, right? So how do we actually manage these problems? These are the practical guidelines for using here one-sample t-tests. So if your n is less than 15, and this is for a one-sample t-test, again, which we're probably not going to use that often, but if that is the case, then you can use t-procedures if the data are close to normal. But if you have a sample set of data that looks not normal, or if outliers are present, then don't use the one-sample t-test in that case. But normally we like to collect more data than just 15 observations or less. Actually, I think I've said this before, but people will often ask me as a piece of advice, like, how many subjects should I run in my experiment? And I often say, well, about 20. It sounds like a good number. In our next set of lectures, we're going to look at a way to determine like how many subjects you should run to give you the best shot at getting a significant result if there's a difference to be found. So there's actually a specific number you can put on that based on a particular method. But my rule of thumb is, say, like 20. The rule of thumb here in this user's guide says, well, if n is between 15 and 40, and remember this is for a one-sample t-test, then the t-procedures can be used except in the presence of outliers or strong skewness. So this means even if your data are not close to normal as you see them, go ahead and use the t-test procedure. And if you're above 40, it doesn't really matter if there's skew or not. Just go ahead and roll the dice, and it should come out okay. These numbers differ a little bit depending on whether you're using one sample or a two-sample t-test. In a paired samples test, remember the number of observations in each sample has to be the same, and then you wind up with a one-sample t-test at the end of the day. So like with that paired samples test we used for the Calgary and Toronto high data, both January and July have 31 days, and our degrees of freedom wind up being 30 because of that. But the end there is basically 31, right? That's the number of days in each city for those months. If you're looking at, that would put us in the middle of this second sort of criterion here, between 15 and 40. What you can get for two-sample tests, though, is number one, the number of observations in each sample can be different, which is nice and convenient because sometimes it's easier to get speakers from Calgary than it is to get speakers from Edmonton or what have you. But you can apparently use smaller samples if you keep the two sample sizes equivalent. That situation doesn't come up that much, or people, I don't think about that a whole lot when they're running stats. They just kind of like throw a t-test at the problem and hope it all works out. But for two-sample t-tests, the guidelines for n above can be replaced with n equals n sub a plus n sub b. So these are the number of observations in the two different samples. And as I said before, like I have this rule of thumb, like if you run a perception experiment or whatever, go for 20 subjects. So then if you get 20 subjects in each group, then you wind up with a total n of 40, which basically gives you, puts you in this region here where you can use a t-test no matter what. Although in some cases, you're not going to be even thinking about using a t-test. But if you do, you should be okay with that size of an n. That's all I'm going to say about the user's guide. You can keep that in mind as you do your homework for the next homework assignment. Another thing you can keep in mind as you actually go through life in a practical way, trying to do research and generating statistical analyses on the basis of your data, is that sometimes the t-test will not be appropriate and you can't use it according to the guidelines. And in those cases, what you can do is run what is called a nonparametric test. And the one that's appropriate for the sort of normal situation where you'd be thinking about running a t-test is called a Wilcoxon rank sum test. And a Wilcoxon rank sum test will compare two sample means, but it does so non-parametrically. And what I mean by that is that it's not going to make any assumptions about whether your underlying distribution is normal or skewed or what its mean is or standard deviation or anything like that. It's not going to make any assumptions about the parameters of that population. And instead, it's just basically going to kind of put the data in a rank order and try to generate a p-value that you can draw inferences from on the basis of that. Okay, so you can use non-parametric tests if the properties of your samples don't satisfy the guidelines for using parametric tests, which have all these assumptions behind them and which your data might or might not fit. So in a sense, this is kind of like a safer way to run a t-test because you don't have to make those assumptions. It usually winds up being kind of a weaker way of running a test, though, because you're missing out on some of the structure that's in the data when you run your analysis. But I will say we're going to walk through a number of different parametric tests in this class throughout the semester. For each one, there's going to be some non-parametric alternative available to you, which you can use if things get messy. I'm not going to talk about the rest in so much detail as I'm talking about this one, but I just want to give you this one as an example so that you know that there's this kind of out in case you run into statistical trouble. Okay, so I'm going to walk you through the process of using this test to compare the means of the January highs we looked at above. And again, normally you're not going to have to go through the nitty-gritty like this. I'm just going to show you this so you get a sense of how it works. And then I'll show you an easy way to do it at the tail end. But what a Wilcoxon rank sum test does first is it wants to rank all of the data in your samples and then come up with sort of the overall combined rank for the two different samples you're looking at. So the first thing I'm going to do here is put all of the high temperatures into one big vector, combining both Calgary's and Toronto's. And then I'm going to create a vector of labels saying the first 31 of these are from Calgary, the second 31 are from Toronto. So just like associate those as you need to. And then it's going to combine both from lowest to highest using this rank command right here. So it's going to rank all the January highs. And if I take a look at what that does for me, it's basically converting these raw numbers into a rank. So negative 1.7 was the high in Calgary on January 1st that year. That is the 39th highest temperature in this data set. Maybe we can look at, or maybe it's going the other way around here. So yeah, so the high numbers are higher temperatures. The low numbered ranks are the lowest temperatures. So I think this is negative 21.7. We had a day in Calgary where it did not get above negative 21.7. And I survived to talk about it and teach this class on top of that too. So you can do it too. It's just sometimes kind of hard. Anyways, what this is going to do is going to convert each raw number into a rank according to how it measures up with the other raw numbers in this data set. But we're going to lose some information here, right? So we're not going to get like the difference between negative 21.7 and negative 20.5 is 1.2. We're just going to go from that's the lowest one and that's the second lowest one, right? And so this test will add up those ranks for both samples, or in this case, both cities. And it's going to say, well, Calgary's overall rank was 975 if you add up all the ranks for its days in the month. And Toronto's was 977. So those are both pretty close in terms of rankings. So there's probably not a significant difference there. And we've seen before at the t-test there shouldn't be. What does the Wilcoxon rank sum test tell us, though? Basically, it's going to spit out a p-value based on whatever difference there might be between these two numbers. I've got some verbiage in here about how we'd have to look this up in a table back in the old days. But for now, we can just actually run the Wilcoxon test this way. And if there are ties in your data, it's going to give you a warning message. You don't have to worry about that so much. It's going to give you this Wilcoxon statistic, a W statistic, and it converts that into a p-value, which is very big. The biggest p-value you can get is 1. This one is 0.9944, so it's 99.44% pure, I guess. Either way, it's not significant. So it's not saying that there's a difference between Calgary and Toronto in terms of January highs for this year, right? This p-value, though, is much bigger than the ones we saw before. Like I said, this tends to be a weaker test, these non-parametric tests. So if we compare it to just our Welch correction test, that had a much lower p-value of 0.64. Still not significant because it probably shouldn't be, but it's going to get us closer in that direction. So for that reason, I generally say if your data meet the criteria, you should try to use a parametric test if you can. But if you can't, there's always going to be an out for you by using one of these sort of non-parametric tests, which make less assumptions or fewer assumptions about your data. So there's more than one way to skin that cat, I guess you could say. Yeah, so the other thing is, at the end of this, I've got this little note about as long as the test satisfies criteria for use with a particular set of samples, you can use it. But you have to play the game fairly, right? So you need to decide what your statistical approach is going to be before you take a look at a p-value and say, oh, this one is the biggest one, the paired samples test, I should use that. You can't do it that way. You have to come up with a decision based on principles and reason before you collect your data and analyze it, and then say, I'm going to run this and just accept the p-value that it gives me. I can't just go looking for significant p-values because that is p-hacking. And that sort of thing might wind up leading you to believe that ESP is real, even though it's not. I can't read your mind. You can't read mine. We just have to talk to each other. We have to run the test fairly. So that's all I'm going to say for now about that. However, I am going to say something about predicting the future in the next lecture when I talk about power analysis, which, like I said, is an approach or a method you can use to try to determine how many subjects you should run in your experiment to get a significant effect if one is likely there in the underlying structure of the data. Okay, so we can look forward to that. It hasn't happened yet. I don't know how it's going to turn out, but it'll probably be educational and maybe a little bit entertaining as well. So I'll see you guys then. And just keep in mind this last moral of the story. Run these things fairly. Otherwise, you're not doing science. You're just wasting everybody's time. Okay, see you next time.